All right, when x is 0, your first derivative is 3, your second derivative is -2. What is happening? So it's increasing slope and concave down. Okay, everybody agree with that? Trey? Because the first derivative is positive. Okay, what's happening at 1? It is a max, and it's concave down. Why?
Because 0, the first derivative is 0, and the second derivative is negative.
First derivative is 0, which means it's a critical number, a max or a min, and it's a max because it's a concave down situation. What's the point at 2? What do we know about that?
Decreasing slope and interval inflection.
Decreasing slope and a point of inflection. 3, what's going on?
Decreasing slope and concave up.
Okay, so you can do that. Okay, here you go. Here's your optimization. I'm sorry. You guys were struggling a little bit with this before lunch.
All right, I'm good.
Good.
Appreciate it.
Optimization. So if you aren't paying attention right now, you should pay attention now. All right, a piece of cardboard is 10 inches by 10 inches and it's folded into a box with a lid. What are the dimensions that the box has that maximizes the volume? We want the maximum volume. And what is that maximum volume? Okay, so I have a few dimensions down here. This is x and this is x. So each corner is x and x. So there's an x there, there's an x there. If this is 10 long, and we take away 2 x's, then I have 2 spaces left to cover. So if I divide it by 2, I get 5 minus x. So if this is 5 minus x, this is 5 minus x. That probably won't be on the test, the 5 minus x's for you. I might have some x's down in the corner, but that's about it. Okay? So, do you understand where I get the 5 minus x? Because this whole side has to add up to 10, right? So, x plus 5 minus x is 5. X plus 5 minus x is 5. 5 plus 5 is 10. Okay? So, if this is x and this is x, what's this right here? How long is that? 10 minus 2x. Thank you. 10 minus 2x. So basically, this is the base of the box. These are the sides. This is a side, a side, a side, and a side. This is the lid, and this is the bottom. So if you would fold it up, it would be a folding box with a lid that would go over the top. Okay? So those of you who brought Krispy Kreme donuts, it's like one of those cardboard boxes that fold up. Yeah, yeah. There's all kinds of Krispy Kremes Saturday around here. All right. So, how do we find the maximum volume? Well, what is the volume function for this? Volume is base times width times height, or length times width times height. What's the length of the box? Length of one of the sides. 10 minus 2x. What's the length of the other side of the base? No.
You guess.
If one side is this, what's this side? 5 minus x. What's your height? What's when you fold up the little things? When you fold up the little parts, what is that? X. Dude, do you see where when you fold it up, it would be x?
I see it.
Okay.
I don't know.
So now what we have to do is multiply everything together. Okay, so let's FOIL these two first. So it's 50, outers is minus 10x, inners is minus 10x, last plus times last is plus 2x squared. All that is times x, and then it's 50 minus 20x plus 2x squared. If we distribute the x through there, then the volume is 50x minus 20x squared plus 2x to the third. That would be the volume of it in terms of x. Okay, we good with that?
Is that just the answer?
Oh, God, no.
Okay.
That's the volume function. We want to maximize the volume, so we need to do what? Find the first derivative. What's the first derivative of the volume? 6x squared minus 40x plus 50. We just switched the order. What do we do with the first derivative? Set it equals 0. If we factor out a 2, we get 3x squared minus 20x plus 25 equals 0. 2, basically, if we divide by 2, it cancels. Okay, so we're left with that. Does it factor? Might. I'm not sure how it does, but it might. Like 3x minus 5 and x minus 5. So I get 3x squared minus 15x minus 5x is minus 20x plus 25. There we go. So x equals 5 or x equals 5/3, right? If what? Okay. If x is 5, what's the dimensions of the box? If x is 5, what's the dimension? If x is 5, what's the dimensions of the box? 0 by 0 by 5. Can you have a 0 by 0 by 5 box? Boom. That's not it. So 5/3 must be what x is. So what's the dimensions of the box? Well, what's 2 times 5/3? No, it's 10/3. So 10 minus 10/3 is the same as 30 minus 10/3 or 20/3. 20/3 is the same as 2 2/3. No, not 2 2/3. 8 2/3. Okay. It's 6 2/3. Thank you.
Make this a Friday question, please.
Probably. All right. If we put 5/3 in for the other side, so it's 5 minus x. So 5 minus 5/3 is 15/3 minus 5/3, which is 10/3, right?
Yep.
Which is find the dimensions, which is like 3 1/3 inches. And the other side is 5/3, which is the same as 1 2/3 inches. So the height is 1 2/3, the length is 6 2/3, and the width is 3 1/3, and they're all inches.
It's the H always gonna be just the X.
Yeah. Okay, what is the volume then?
Multiply all of them.
Multiply all three of them together. And I don't know what that would be. Somebody would have to multiply it out.
About as big as this round, I would assume. I think it's like maybe like 4,000 inches, like what inches? I can't even ponder what
6 2/3. That's a little smaller than a Krispy Kreme's donut box. 6 2/3 inches. 6 2/3 inches is like this.
No, it's gotta be like that.
Trey, a ruler is this big. That's 12 inches. 6 2/3 inches. It's a little box, Trey. What'd you get, Allie? What? But with all the thirds involved?
Well, all I did was say, it's like 35 over 3. Wait, it's like 37.03.
It's like 1,000 over 9 if you multiply them.
Oh,
27 over 27.
You're adding.
1,000 over 27.
Or 27, yeah. 27, sorry. 1,000 over 27, which is what?
37.037.
So I was right.
37 and so many 27ths of an inch.
So that's going to be your final answer, 37.
Sure. 37 point something, 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 or 37 and so much of a fraction, yeah. Okay, a store is going to fence off an area of its parking lot to display outdoor items. If 100 foot of fencing is used, what's the maximum area that can be enclosed if they use the wall of the store as one side of the enclosed area? So they have a door coming out from the store that goes into the fenced-in area, so people just don't walk off with the outdoor items. Okay? So, how do we figure this out? Well, what are we maximizing?
I'm taking a guess, bro. You can be mad when I make you start.
The area. Wait. Perimeter.
What's the word that follows maximum up there?
Area.
Area. It says, what is the maximum area? What are we trying to maximize? The area. So the area is what? What's the area? Length times width or whatever. Yep, base times height. So let's just use length times width in this area, this problem. Now, they're using 100 feet of fencing. Is that area? No, that's what? Perimeter. Now, if they use the wall as one of the sides, do we count that wall for the perimeter? So how many widths are involved in this? How many widths? 2 widths and 1 length. So the perimeter is 2 widths plus 1 length. So 100 is 2W plus L. What's the easiest variable to get alone there? L. So the length is 100 minus 2W, right? Plug that in for L of the area formula. So the area equals 100 minus 2W times W. Perimeter. We're going to get to the first derivative here really quick. So the area is 100W minus 2W squared. That's the area formula with just one variable instead of 2 different variables. Now, what do we want to do at this point to maximize the area, Nate? I just asked you a question, Nate. No, you're...
No, Breeze thinks that we're finding the perimeter.
No, I'm not. I'm just telling you the answer.
You said
Breeze, what is the answer?
I don't know that.
He said 25, 25, and 50. That's what he said.
And he's correct.
For the perimeter, right?
No, for the two sides, he is correct. And then if he multiplies them together, he gets the area.
Yeah, but that wasn't the answer before.
All right. So, what's the first derivative of the area is a question that I wanted you to basically give me.
100 plus minus
Don't write it that way.
Equals.
0.
So if we move 4w to the other side, 100 equals 4w.
25.
So the width is obviously 25. And then if you plug 25 into there, the length is 50, like Bree said. So the area equals
You never said that.
1,250 square feet.
You said we were finding the perimeter.
There.
Oh.
Freeze.
Apologies.
You will have to study for this. Even though you just totally nailed this question, don't think that you can just get by without studying anymore.
You just made his head super big. Something's gotta be.
But he nailed this one. You guys, all three of you have to admit he nailed this one.
The thing is, though, that was super easy. I was just thinking
That was the easiest optimization problem I've ever seen.
Yeah. We were all thinking it had to be harder. Like I could have given us.
'Kay.
You got it wrong then.
I don't think so.
I don't think-
Actually, this was a college calculus question for both Megan and Derek on their final test. Because they said they had this one. Because we studied that one.
You could be in college calculus.
Well, this is a college calculus class. Basically, if you pass the AP test, you get 5 credits of college calculus. A 5-credit class. You know how much a 5-credit class costs at college?
What if you don't just waste your time?
$1,500 for a 5-credit class. So if you pass this $100 test, you just saved yourself $1,500.
14. I was gonna say I don't.
What if
You're
I
not
don't-
out there.
Let's
You forgot to take the first.
What if I don't
Wait,
have
what's
to-
like 15 times cheaper?
What's that? That's exactly what
This test is to test out of calculus,
This is
basically.
your one chance.
This is your one chance.
What if you like fail it?
All right. Here's another fun one. Given x squared plus y squared equals 25, what's the slope and concavity at the point 34? There you go, Breezy. First and second derivative. So what's the first derivative?
First derivative is 2x.
2x
Oh, is this
Plus y.
plus
dy
2y dy dx. You guys are on fire. Equals 0. You guys are awesome.
You're shocked. When did we learn this?
This was Sal Khan gave you all this. I ain't giving you this on the AP test. You know how Sal said which step was wrong? You know? Well, you got to do your own derivatives in this. All right, here we go. So how do we find the derivative? Well, you get dy dx alone, right? How do we get dy dx alone? You subtract 2x, thank you.
Sorry. And then divide it.
So dy dx, the first derivative is negative x over y. Okay? So, if you plug the points 3 and 4 in there, what is the slope at the point 3, 4? Thank you, Nate Ricky, for opening up your mouth. It's just negative 3/4. That's the slope. Okay? What's happening to that line at that point? It's decreasing. It's a decreasing slope because it's negative. Okay, now what are we going to do next? Second derivative, dy d2y over dx squared equals, what do we have to do? It's a fraction. Quotient rule.
Oh, no. I burned that.
So it's y times a negative x. First derivative of negative x is negative 1, right? Minus
Wait, what?
negative x times the first derivative of y, not 1, dy dx over y squared. Oh. Where's that from? That's the quotient rule.
Thank you.
From the first semester. You have to remember from this one right here. This one. The denominator times the first derivative of the numerator minus the numerator times the first derivative of the denominator over the denominator squared. Quotient rule. This is real. All right. Now, Nate, Ricky, we should do some substitution. What should we substitute? Oh, no.
Put the -3/4 in for dy.
There you go. So negative y plus x and then negative 3/4 over y squared. Let's do some more substitution. I wanted to do that in the first step so you could see what we're doing. And now let's substitute everything else in. So what goes in for y?
4.
So negative 4 plus 3 times negative 3/4. Oh, no. It sure looks like positive to me. Over 4 squared, which is 16. So negative 4 minus 9/4 over 16. Okay. Do I even need to find the number? No. What is this number? Negative 4 minus 9/4. So it's like negative 6 1/4 over 16. A negative over a positive is a negative. It's going to be?
Concave down.
Thank you. There we go. Looking at this function, where is it increasing, decreasing, concave up, concave down?
First derivative.
First derivative. First derivative is 3x squared plus 12x plus 9. Second derivative is,
6x plus 12.
set the first derivative equals 0. How do we solve it? Factor. Take out a 3. X squared plus 4x plus 3. How do the factors work? Say it louder. 3 and 1. So x equals negative 3, x equals negative 1. What are negative 3 and 1? Critical numbers. They are critical numbers, critical points, whatever you want to call them. So they're going to be a max or a min, probably. Okay? All right. So let's just do the increasing, decreasing. So, to figure out whether it's increasing or decreasing, do we use these 2 points? No, we use a point in between. What point is in between negative 3 and negative 1?
-2.
If we put negative 2 in right here, it makes a negative or a positive times a negative, which is a negative. So it's decreasing in between these two. So it's decreasing from -3 to -1. If we go on the outside of it, like -4, what's a negative times a negative? So it's increasing from -infinity to -3, and it's also increasing where? -1 to infinity. That's increasing, decreasing. We good with that? Concavity. Set the derivative equal to 0. So 6x equals -12, x equals -2. So now what do we do? Put -1 into the second derivative. If we put -1 into the second derivative, we get -6 plus 12, which is 6, right? Which is a positive number. So we know this is a point of inflection, right? So -1 is after it. So from its concave up, where it's positive, right? Which is from -2 to infinity. Where is it concave down? -infinity to -2. Concave up, concave down, increasing, decreasing. First derivative, second derivative. At the start of the day, this would have been a kind of a difficult problem but after we get this far,
Yeah, that's easy.
it's fairly easy
I got
now.
a question, just before
Yes?
we move on. So you put in -1 to find concave up, and then.
Or I could put in a -3.
So how would you find concave down?
So if I put in a -3 in right here,
Yeah, I get that.
You
I
get a
understand
negative
how-
number.
I understand how you're finding the numbers.
okay?
So you put in the 1, you get -6.
You get positive 6. For -1.
If you put in a -1, you get -6 plus 12, which is a positive 6.
Yeah.
So a -1 is to the right of
Yeah.
-2. So it's a number bigger than that.
And
And it's a positive number, so it's going to be concave up. Where the second derivative is positive, it's going to be concave up.
So then did you put in? So then you just know everything to the left is concave down?
Yeah, well, yeah, because I put in a number like -3 to the left of -2, and that's
I
negative,
got you.
and so that has to be concave down.
Okay.
I don't know. I don't think so. If the first derivative of the graph, if this is the first derivative of a graph, where is it concave up? If this is the first derivative of a graph, where is it concave up? Where the slope is positive.
Yeah, so it'd be -2 to 0.
-2 to 0, it's concave. Well, -2 to about here. So, and this isn't the greatest graph, but -2 to about 0.5. And then, where else?
Like 2.5.
2.5 to about 3.75, somewhere like that. Okay? Where the slope of the first derivative is increasing, that's where it would be concave up. You guys are good. I'm glad you guys caught on to that.
Yeah, I totally got that down.
Well, actually, it's increasing slope way down here, so yeah, I could probably say -3 to that, but yeah. Okay.
Where was the other point? Are you back?
Because it starts increasing here. So where the slope is increasing on the first derivative, that's where it's going to be concave up. Okay? Okay, last thing. Where are the points of inflection on this?
0. Points of inflection. That would be 0 in the second derivative, correct?
Correct, sort of. And this is why I put this question on here so I could explain it. You would think 0 and 2. Definitely 2 is a point of inflection. Why? Because it's 0, but what else? Look around it. The concavity goes from positive to negative, so that's why it's definitely a point of inflection. Okay? See how it goes from positive? It kind of flattens out, you could say, and then goes positive again, so it kind of has like a ripple effect. Oh, that's drawn wrong. That's drawn wrong. So it's concave up, and then it kind of goes like that, and then continues concave up. That's kind of what's happening here. Okay? If it doesn't change from concave up to concave up, I mean, the concavity is both positive there. This is really not a point of inflection. It's just kind of a hiccup there. It's where we had the double root for the second derivative on some of those where we had the double root and it wasn't there was no points of inflection on those questions from Salcon. That's kind of what's going on here. This is a double root. Now look over here. Okay. How 2 is? Because the second derivative is 0 and it changes from positive to negative, so it's concave up here and it's concave down here where it changes concavity. Where it changes concavity, it's a point of inflection. This is the first derivative. So that's decreasing slope, increasing slope, increasing slope, decreasing slope. Now, what happens at 4? What the heck is going on at 4? That's undefined, undefined. Yes, it's an asymptote. Now, if concavity changes at an asymptote, it is a point of inflection. And this has been argued, and it's been different in different textbooks. But the AP says that if concavity changes at an asymptote, it is a point of inflection. So we have to mark that as a point of inflection. Okay? So concavity changes, point of inflection. Concavity doesn't change, not a point of inflection. Just because the second derivative is 0 does not guarantee you a point of inflection. Okay? That's what that question's asking. And hey, that's it. Go where?
You should have seen some of the tweets he had. He was just like bashing people that would say there's an asymptote and it changes concavity.